Hello, welcome to the second part of this series of two lectures on climate change. All right, so last time in part one of these lectures, we went through a few things. We learned about the difference between weather and climate. So weather being very, in terms of sort of a short period of time, so in a small area, so it's raining today in London, for example, um, etc., or it's snowing in Philadelphia, as examples. On a specific time scale within a specific small geographical area. Climate, though, is averaged or a composite of weather. So think of monthly mean high temperatures for an area, or think of annual statistics on weather for an area, it would be temperature or air pressure, etc. And the important thing about climate data is you look at trends. So you can look at trends both through during a year, but especially annual changes or even decadal changes. And that's where we start to see things where with these trends in terms of climate change or the current situation of global warming, um, certainly decade on decade, or if not year on year. Um, Last time we also looked at various sort of regional climate controls like mountains, etc., proximity to oceans. And then we went on to the important subject of how humans influence the atmosphere. And it's all to do with greenhouse gases such as carbon dioxide, for example, and the greenhouse effect. So we learned about the science behind the greenhouse effect and global warming, which kind of ensues from that. We also learned about records of past climate change. So think of things like ice cores, how ice cores can be used to reconstruct climate, and also deep sea sediment cores and things like tree rings. Some of those things we're going to revisit for a little bit more detail, such as ice cores and deep sea sediments. And I'd like to tell you some sort of more information to do with how those climate records, those paleo climate records, are reconstructed, especially with the use of isotopes. And all will become apparent later when we get to that part. Okay, so climate change part two. What are we going to cover in this lecture? First of all, I'll introduce the subject of the property called insolation. It's the amount of radiation striking sort of the ground on Earth, a certain sort of square area of ground, and Earth-Sun relationships, basically how insolation can change over time. And it's all to do with the geometry of the Earth and its juxtaposition to the Sun, and how that changes over time. And we'll see that the Earth has an eccentric orbit. It's not quite, a circle, but sometimes it's much more eccentric. Um, so in other words, it can be further away from the sun. Therefore, less coming solar radiation reaches us, therefore cooler climates. And these cycles, and there's actually three of them we're going to cover, are called collectively the Milankovitch cycles, after the geophysicist who first realized this. Um, then we'll go on to global climate change in terms of long-term climate change. So over millions of years, or certainly hundreds of thousands of years, and short-term climate change in terms of, yes, over thousands of years again, but also over centuries as well, and shorter timescales. And what governs those and what controls these natural climate changes. So we'll be looking at, again, the natural variation in climate. But with the short-term climate change, we'll also look at anthropogenic forcing, as it's called. So how human activities force the balance between incoming radiation and outgoing radiation, basically the greenhouse effect, how they make that stronger. We'll look at, in terms of short-term climate change, a lot about anthropogenic effects on climate, which we definitely have. That's just without a doubt now. And finally, projected future climate change, over the next generation. Certainly, there's lots of models now where we project climate and the changes that we'll see in climate, or likely to see in climate, say by the year 2100, the end of this century, under different scenarios. And those scenarios are generally associated with different emission pathways, or different basically amounts of greenhouse gas emissions from burning of fossil fuels, for example. And basically, there's a best case and a worst case scenario. So, which will and I'll show you kind of the differences between those models in terms of a temperature increase this century. Okay, so let's start off with the first topic, which is insolation. Insolation, to give you a definition, is the amount of incoming solar radiation per unit area of the Earth's surface. So how much how much solar radiation, strikes, says, the Earth's surface, say a square meter. So solar radiation, it comes through us through the vacuum of space, and its heat's transferred as solar radiation. And here you can see the Earth and the Sun. So remember, we're just about the exact correct distance, well, we are the right distance from the Sun to support life, because we don't get too hot, we don't get too cold. We're just in the right orbit, essentially, to be within that temperature range of sort of maximum and minima for life on Earth, essentially. So the amount of insolation is a major control on short and long-term climates. And as we'll see, especially with long-term climate change, this insolation values do change with time, because, as I said, sometimes we're actually further away from the Sun over a longer time scale, and sometimes shorter. It varies. Okay, so insolation and Earth-Sun relationships. First of all, let's think about how the Earth moves. So first of all, it rotates. Our planet, planet Earth, rotates on its axis. That's a daily cycle. So every 24 hours, it has one rotation, and gives us, a night and day, etc. So there's that. Also, it orbits the Sun every year. So that's another motion of our planet. The seasons, so why we have spring, summer, autumn and winter, why we have those seasons, and seasonal variation in climate, it's all to do with the fact, the top point there, that we rotate on its axis. But about the axis, we actually aren't, planet Earth isn't straight up and down, it's actually tilted on its axis by 23.5 degrees of an angle. And that is why we have seasons, as we'll see in some diagrams I'll show you. Basically, during the northern hemisphere is pointing towards the Sun. If this is the Sun, the northern hemisphere is pointing towards, the axis is pointing towards the Sun during the summer. Therefore, the Sun's overhead, and there's more insolation per unit area on the ground. Therefore, warmer temperatures. Therefore, summer. But then, when the planet goes around the Sun, to the other side, it's now pointing away. The axis is pointing away from the Sun, and therefore, in the northern hemisphere in this case, and therefore there's less insolation, and we have winter. That's it in a nutshell. But I will, rather than do my two hands, I'll show you that in a diagram, which will be a lot more self-explanatory. So seasons. Result, as I said, of Earth's orientation to the Sun, and it's something we call the Sun angle, the changing Sun angle. So the axis, as I said, is currently inclined. As we'll see, it does change over thousands of years, but for now, let's just say what it is now, which is inclined by 23.5 degrees of an angle. The axis is always pointed in the same direction. So you have the Sun, it's always pointed, say, from whatever, if that's right to left, as it goes around the planet, around the Sun, sorry. And the seasons, this changing Sun angle will also change the length of daylight, length of daylight hours as well. Again, we might see that in the diagram. So this Sun angle, so the relationship of Sun angle and intensity of solar radiation. And so here, three sets of diagrams. The far left is sort of around the equator. The middle one is sort of the mid-latitudes, and so sort of Europe, sort of east coast of America. And the right-hand one is the high latitudes. So, for example, the Arctic. So on the left, we have incoming solar radiation straight from above, let's say at the equator. And at the equator, you know, the sun is right above you, basically, in the sky. And it shows here that you know, per unit area, 1 unit coming in at a 90-degree angle, sun angle, and that's the 1 unit, basically. It's at right angles. It's coming in at normal to the surface. In the mid latitudes, it's coming in here at a 45-degree angle, the sun angle. And here you can see, because of that, as it's coming in, it's smeared, like you can see the sort of flashlights at the top right to kind of show you that energy is smeared over a larger area, a larger unit area. Therefore, per unit area is actually less energy, less solar radiation incident on the planet's surface, therefore cooler. Here, there's only half of the original, you know, it's over 2 units instead of 1 in the very high latitudes. So again, less, you know, therefore 50% of the value of insolation per unit area now. So the key thing is, it says at the bottom here, the higher the angle, the more intense the solar radiation. So the higher the angle, 90 degrees being obviously the highest over the tropics and near the equator, for example. And this changing angle is also due to the fact we're not a flat Earth, despite those people who believe that. We're a globe, we're a sphere. Therefore, as the sun strikes our planet, at some point it's straight overhead, but at some point it's at an angle as you go around the edges of that sphere to the north and south. So here's the Earth on its angle of 23.5 degrees, 23.5 degrees. And here you can see the sun to the left, and the sun's rays coming in, incoming solar radiation near the equator, or within the tropics. It's virtually always straight overhead, so it's a very high sun angle, therefore much more intense incoming insolation values. As you go to the higher latitudes, that angle, the sun angle, is becoming less. Therefore, the same amount of energy, it's always the same amount of energy coming in, solar radiation, but now it has to be spread over a wider area. Therefore, per unit area, there's less insolation. And then, you know, on the equator, on the very high latitudes, there's even more, it's over even higher surface area. That energy has to be spread over. But also, you'll see it shows the atmosphere in this diagram, and so, you know, it envelops the world, and you can see that radiation, that incoming solar radiation in the high latitudes, has to go through a longer distance before it gets to ground. Therefore, it's got more chance, or what does happen, more of it gets reflected, more of it gets absorbed before it actually gets to the Earth's surface, from where it can be re-radiated, remember, as terrestrial radiation, which then gets trapped by greenhouse gases and warms the planet, etc. So in other words, it's cooler. So it's a sun angle plus this distance going through the atmosphere at the acute angles at the top and the bottom. It shows here, by the way, the 2 tropics of Capricorn and Cancer, the 2 lines sort of north and south of the equator. Actually, it doesn't, but there are two tropics, because you know, the different values here of Capricorn and Cancer above the equator. I forget I think they are 23.5 degrees north and south. Anyway, within that zone, at some point, the sun can be directly overhead at some point in the tropics. Okay, so feeding back from that last diagram, where, you know, the higher intensity of insolation was around the equator and the tropics. Here you can see this diagram shows sea surface temperatures around the world and the variation. So SST at the top stands for sea surface temperature. And, you know, the highest temperatures, you know, this is in Celsius, you know, are, you know, sort of 26, 27, 28 degrees around the equator. So, you know, warm water, in other words, a lot of heat in the world's oceans, caused by that very intense sun coming directly from above and warming the world's oceans in this case. As you go further north, and further south to higher latitudes, you'll see those temperatures rapidly drop until they're almost just above zero by the time you get into the Arctic Ocean or the Southern Ocean near Antarctica. So that's why, because of the smaller sun angle up there, and more of the incoming radiation is being reflected or absorbed through the atmosphere, hence the lower temperatures. So that's really what changes. That this latitudinal change in temperature is caused by changes in sun angle. That's the key thing. That temperature, it's not quite as simple as that, because temperature is heat, on our planet is also transferred through ocean currents and through the atmosphere, basically from the warm tropics to north and south through global circulation and patterns, and also through ocean currents. They also are very good efficient in transferring heat, say northwards in the Atlantic or southwards in the Atlantic, away from the equator as well. Okay, going back to the Earth-Sun relationships and the sun angle, this slide shows what would happen over midsummer, or what we call solstice. So that's the longest day, and the winter solstice, which is the shortest day. In this case, these diagrams represent for a latitude, so a mid-latitude. So at 40 degrees north, I think that's kind of sort of east coast of America, sort of northeast of the States, I believe. 40 degrees north latitude. So sort of mid-latitude, it's in the mid-latitudes, like I say. So here, for that specific latitude, the sun angle on the summer solstice is 73.5 degrees. That's the highest angle that you can get at that latitude. It's never directly above, in other words. And the shortest, smallest angle is at the midwinter, the winter solstice, which is December 21st, and that is only 26.5 degrees. So the sun doesn't get far off the horizon, basically, during around the 21st of December. And as you go further north, by the way, or south, at the very high latitudes, that sun is dropping in the sky on the winter solstice more and more, and eventually, actually, when you're in above the Arctic, you can have days of complete night, or days of complete sun as well, conversely. But you do have this dark period in the very high latitudes. So that's the sun angle for between the two seasons of summer and winter there. So what gives you why do we have seasons? Just to show you, I kind of described it earlier with my hands and the sun, and the Earth's axis, the tilt of the axis. So remember, we tilt at 23.5 degrees. So this diagram shows during for the northern hemisphere, for example, on the left. So the summer solstice, June 21st. Here, the northern hemisphere is pointing towards the sun at that point. Therefore, more direct, higher intensity insolation values, and therefore summer. The other extreme, 6 months later, it's pointing away. Remember that it always points in the same direction, the axis, as it revolves around the sun. And here, so it's pointing away. Therefore, the northern hemisphere has less insolation. You can see as well in the northern hemisphere here, once you get above that final the Arctic Circle here, during the winter months around December 21st, it's actually permanent darkness once you're above that line, the Arctic Circle, in the midwinter. Okay, so that's what gives us our seasons. The fact that we have on up and down our axis, straight up, we're tilted at an angle. Okay, all right, so let's go on to talking a little bit about insolation and longer term cycles and what affects the amount of insolation sort of striking our planet, or striking how much solar radiation reaches our planet as well. It's also to do with things called Milankovitch cycles, named after a scientist, Milutin Milankovic. He was a Serbian astrophysicist born 1879, lived till 1958, and especially later in his career, in sort of the 40s and 50s, he did a lot of great work on kind of working out, unraveling, astronomical observations that showed that we check there's various cycles that goes on, including what's called eccentricity of our orbit, the Earth's orbit around the sun, which means at some points we're more elliptical and other times less elliptical. And when we're more elliptical, that means we're going to be further away from the sun, therefore less incoming solar radiation, because it gets less with distance from the sun, and colder temperatures. And it's basically this, as we'll see, what drives ice ages or glacial periods, glaciations, and interglacials. This big this cycle that goes on, which we'll come on to. All right, so the three Milankovitch cycles are the eccentricity, obliquity or tilt, and precession. And each of these cycles, which happen on a sort of multi-thousand-year cycle, which I'll give you the actual time scale for each one, they result in variations in solar energy reaching Earth. So therefore, it changes climate. It's a natural cycle which changes climate on our planet on the different time scales, as we'll see. So eccentricity is certainly, I would say, definitely the most important one, but the other two also affect variations in solar energy reaching us, but also the bottom two also affect obliquity and precession, affect the strength of the seasons as well, or the severity of the seasons, of severe winters or severe summers, etc., as we'll see. So eccentricity, obliquity, and precessions. First of all, eccentricity. I'm just going to show you for each one what that represents. So here you have low eccentricity of the Earth's orbit, which is kind of where the Earth is often like, but it's also we go through another cycle. So we go from low eccentricity to a high eccentricity on a 100,000 year cycle. So every 100,000 years, we may be at a stage where we've got a very high eccentric orbit around the sun, and therefore cooler temperatures. So if you look at the bottom right diagram, graph there, it shows values of eccentricity on the y-axis and the vertical axis, and then on the x-axis, the horizontal axis, it's thousands of years ago. So present day on the left, going back 100,000, 200,000, 300,000, 400,000, 500,000, 600,000, 700,000 years ago. And these peaks go up and down in terms of eccentricity of the orbit around the sun. And you'll see it's every 100,000 years. And what do those peaks mean? Well, basically, when it's these high peaks are basically the extremes of it'll be colder temperatures, and as we'll see, this is basically what causes the glacial interglacial cycle, which has been happening on Earth, certainly very much so for the last 2 million years. So every 100,000 years you have an ice age, essentially, or a glacial period. Or every 100,000 years you have an interglacial. Currently, we're in the middle of an interglacial, which is typically between sort of 10 and 20,000 years. We're 10,000 years through, so we might be 2/3, maybe halfway through an interglacial. And it's all controlled ultimately by these Earth-Sun relationships and these, in this case, eccentricity cycle. Okay, the other two cycles, Milankovitch cycles, are firstly obliquity or tilt. So the obliqueness or tilt of the Earth's axis. I said we're currently 23.5 degrees, but that actually does change over a long time scale. The angle of the Earth's tilt of the axis. So it can be a higher angle or a lower angle. So it actually varies between 21.5 and 24.5 degrees over a 41,000 year cycle. So when it's at a higher angle, say even up to 24.5 degrees, that's going to make it pointing more and more towards the sun during, say, the northern hemisphere during the summer, and that, or further away during the winter. In other words, the higher the angle, the more severe the seasons, the more extreme in terms between winter and summer. So that affects global climate very much so. The third one, and you can see the cycles on the bottom. This 41,000 year cycle on the bottom. It goes up and down. The third one is the shortest time scale. It's every 23,000 years, and it's called precession. And it's precession of the Earth's axis. I said we're always pointing kind of at the same angle. Yes, we are, but it actually does as we orbit the sun. But actually, there's also a cycle as well, what we call precession. So the Earth is rotating, but it also has this wobble. So think of an old toy called a spinning top. It's very much like a spinning top. If you've ever seen this old toy, you spin it and it goes round, 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 but it also kind of wobbles around as you do it. You can do the same thing when you spin a coin on a table. You'll see it do that, but you also see the wobble, especially as it slows down. So the same thing happens with the Earth on this 23,000 year cycle, this precession of the Earth's axis. So currently, we're pointing towards as the Earth rotates, it's also pointing always, you can see on the left, to Polaris. The North Star. Everything kind of rotates that. You can see that in this photograph in the middle. By the year AD 14,000, so here we are in 21st century. So another 12,000 years from now, fast forward, we'll actually be pointing towards Vega, another different star. So that will be the North Star, not Polaris at that point. All right. Put all those three cycles together, you get this pattern again over the same time scale of sort of 700, 800,000 years, and you can see again much more obviously now the 1, 2, 3, 4, 5, 6, 7 peaks every 100,000 years. You get a glaciation, basically an ice age, because there's less insulation essentially during those times. Yep. Okay, so summarize insulation. The Earth's orbit is slightly elliptical, and its rotation axis lies at 23.5 degrees to the normal, to the ecliptic. But the key thing is that it's slightly elliptical rotation, and that changes. This tilt is responsible for the seasons, as we see. This is the tilt in the axis. That's what gives us the seasons. And the long-term cycles of the Earth-Sun geometry, or what are called Milankovitch cycles, change the contrast between the seasons and the amount of solar insolation. So, for example, especially eccentricity changes the amount of solar incoming solar insolation, and the other ones, obliquity and precession, very much change the contrast between the seasons as well. Milankovitch cycles can be thought about as the pacemakers of global climate change. They're like almost the heartbeat, the rhythm between the ice ages, or between the warm interglacial periods every 100,000 years. Although other controls are important, as we'll see, other controls like ocean currents, for example, and various other natural kind of variations with this. Okay, so global climate change. So the Earth's climate has changed many times over a long time period, sort of natural variation. So we have long-term climate change. So on a time scale, we're talking millions to tens of millions of years in scale. So really kind of going back into geologic history. And short-term climate change, and here we're thinking sort of tens to hundreds of thousands of years in scale. Sometimes, depending on you read, the boundary between those varies. So some people put Milankovitch cycles into long term, some people put Milankovitch cycles into short term. It depends on what sort of time scale you're kind of thinking of. So paleoclimates, which literally meaning ancient climates, so past climates are interpreted by datable Earth materials that are climate sensitive. So we mentioned a couple of these in part 1 of these lectures, but to go over. We will mention those again, but we'll think also about global climate change and long-term things. So what can you use to reconstruct climate change over a long-term period? Well, depositional environment. So sediments are very useful. So for example, and very climate sensitive. So for example, glacial tills. So in other words, sediments laid down by glaciers. They're called tills. Basically, as a glacier or an ice sheet melts and retreats up a valley, for example, or gets to the front of a glacier, a mountain glacier or an ice sheet, it will dump its load of sediment which it is transporting and carrying within it. So as that ice melts or wastes in place, all the sediment within it will be just simply deposited, and these are called glacial tills. So over a long term, you know, time frame, if you see glacial tills maybe at lower latitudes, it shows you're going for a very cold period of Earth's history. Or if you only see the glacial tills at very high latitudes, it might be warmer. Conversely, if you see evidence of very warm depositional environments like coral reefs, so limestones representing coral reefs, maybe at higher latitudes than currently, it shows it was a very warm period of Earth's history, that the fact that they had, you know, coral reefs in the mid latitudes, for example. So these are very useful, these sedimentary environments and sedimentary deposits to reconstruct long-term climate changes on Earth. Other things, we looked at this in part one, but just to bring it back again, you can use animals and plants. Here's one looking at plants or flora to show changes and cycles in climate. Here relating to the advance of the North American ice sheet and then the retreat of the North American ice sheet after that last glaciation. So here advances in the green, being the spruce forest is further south at that point, and you know, this coniferous forest in the northern part of the United States. But currently, the spruce is coniferous, the big coniferous forests are up in Canada. Now it's during sort of warmer interglacial period. All right, so we covered a little bit of that on last time, but what we didn't cover was the use of oxygen isotopes in reconstructing climate, and they very much really. When we look back at the Earth's climate over the last sort of million years, and we look at the changes in climate and look for direct evidence of that, we very much use these oxygen isotope records. And the oxygen isotope records can be derived from ice cores or from deep sea sediments, as we'll see. So what are they? Well, it's all to do with the fact that oxygen is existent on Earth, exists in two main isotopes of oxygen. There's oxygen 16, so for mass number of 16, and oxygen 18, mass number of 18. So that they're called typically light oxygen, 16O, and heavy oxygen, 18O, the higher mass number. So they're stable isotopes. In other words, they're stable on Earth. They're not unstable isotopes, which would go through radioactive decay to a stable daughter isotope. These are stable. They stay in similar quantities through time. There's no decay. Okay, so water, the light oxygen or water evaporates faster than heavy oxygen. Basically, as the process of evaporation, at the ocean surface. It's the light stuff, as you think probably would, intrinsically, it's a lighter oxygen, lighter in mass, therefore it preferentially will evaporate off and leave the heavy oxygen left behind in the ocean. So how does that mean? What happens because of that during an ice age? So here during an ice age, with a large ice sheet existent during an ice age, you have the light oxygen, the 16O in seawater evaporates faster still. That leaves the seawater behind, the chemistry of it, depleted in light oxygen, and heavy oxygen, 18O, enriched. So there's basically a higher proportion of heavy oxygen left behind because most of the more of the light oxygen has evaporated off preferentially. So that leaves the ratio between 18O and 16O changing. So the ratio increases in the remaining seawater. It becomes more dominated by the heavy oxygen. And how do we see that? how can we actually measure that and record that over time? Well, we look to kind of time capsules of that, time capsules of the ocean water, and we can do that by either looking, well, first of all, it says the shells grown in the sea will reflect the altered. So there's seashells, they organisms with hard parts and skeletons, they produce their skeletons and shells by extracting elements from the seawater around them, including elements like oxygen, to construct their shells. Therefore, those shells, if you measure the ratio of heavy to light oxygen in those shells, it tells you what the sea chemistry was at that time when that organism lived, be it 1,000,000 years ago, be it 100,000 years ago, be it 10,000 years ago. Also, you can measure the ratio between heavy oxygen and light oxygen actually in ice cores, because they also have that ratio. So to go back, during ice ages, to recap, the seas become depleted in light oxygen and enriched in heavy oxygen. I should have really started actually by describing what happens currently during a warm interglacial. You don't have that happening, and why? Normally, when you don't have huge, massive ice sheets in the northern hemisphere or the southern hemisphere, during the last ice age, there was a massive ice sheet covering most of North America. There was a huge ice sheet over the British Isles and over Scandinavia and Northern Europe and over Siberia. So huge areas of ice, much bigger than they are now. It was around about 30% of the Earth's surface was covered by ice. It's about 10% now, land area. Anyway, during current conditions, when that light oxygen evaporates off, yes, it still does preferentially, but then it gets into the water cycle. It goes up into the clouds go over the continents, then it rains through precipitation and carrying the elements with it, and then that precipitation, when there's no ice sheet, simply goes into rivers and back to the ocean. In other words, a cycle. In other words, the water chemistry doesn't change. The ratio stays the same. So it doesn't become over-enriched in heavy oxygen. But when you have large ice sheets, as you go through that water cycle, so it's evaporating the light oxygen, and then when the light oxygen comes down as precipitation, as snow, for example, it gets locked in the ice sheets. It doesn't find its way back to the ocean. So in other words, you're gradually extracting more and more light oxygen and locking it away in the ice sheets. Therefore, the ocean water chemistry will gradually become more and more enriched in heavy oxygen. And you can measure these ratios, these changing ratios between the interglacial and glacial climate using either ice cores. So this diagram on the right shows a time scale from present day at the top in Ka, which is thousands of years back, down to 120,000 years ago. And it shows left in the blue, colder climate to the left, warmer climate to the right, this ice core record. And this core record has been completely derived from, it shows at the bottom, lower ratios of heavy oxygen to light oxygen here, or higher in warm on the left, and on the right it's higher ratios. And this is for ice cores, directly measured from the ice core, the ratio from the ice water analysed. As you go down that ice core, be it in the Greenland ice sheet ice cores or for the Antarctic ice sheet ice cores. So that's how we get records. Basically, we measure the ratio between the isotopes of oxygen in an ice core, or we measure the ratio in deep sea sediments. So here now the climate record on the right showing variation is over a longer time scale, about double that. It's almost 2 million years. 15, 16, yeah, but 18, 19, about 18 or 19, no, 1.9 million years, I think that is. Again, cold on the left, warm on the right, showing lots of variations. Basically, every 100,000 years, you've got a cold period, 1, 2, 3, 4, 5 in the last 500,000 years, for example. So 5 glacial stages, and 5 warm periods. So we're currently in the peak in the here, which is to the warm climate. So we're currently in what's called the Holocene interglacial. If you go back in time, the last one was called the Ipswichian interglacial. It was actually warmer than it is now in Britain at that point, around about sort of 110,000 years ago. But anyway, you derive this from, again, looking at the ratios, oxygen isotope ratios, now based from marine shells or microfossils found within these deep sea ocean cores, deep sea sediment cores, and things like this thing at the bottom, which is a type of foraminifera, or just called forams for short. And these things are about 1 millimeter wide in diameter or less, very small organisms. They're basically a type of plankton, and they float around the world's oceans, but they construct their shells out of calcium carbonate. Therefore, they reflect the water chemistry at the time when they lived. So if you can date them, and you can date these things using methods like radiocarbon dating, if it's quite recent, or other types of dating, and so you've got an age, and then you've got an isotopic signature, and you can work out climate. So between ice cores and deep sea sediments, and looking at oxygen isotope ratios, they've really completely transformed our knowledge of and enhanced our knowledge of paleoclimate over the last, going back certainly a couple of million years. The ice core records, by the way, they go back about 700,000 years in the Greenland ice sheet before you get to the bottom of the ground. The Antarctic ice cores, they go back about 1 million years. The deep sea sediment cores go back longer. You're not constrained by the thickness of ice. Now you can go back further, so they can go back several million years from these deep sea sediment cores. Okay, so long-term climate change. I'm going to have to speed up because I don't want this to be too long a lecture. Looking at the time now. Okay, so on a very long time scale, so thinking of sort of geologic time scale over millions to even hundreds of millions of years, here you can see the geologic time scale on the right. So going back throughout Earth's history, we're currently in the period called the Quaternary, which is the last sort of 2 million years. And here again, we go through cold phases and warm phases. We're currently in a cold phase, a very oscillating back and forth between glacial and interglacial, very unstable climate basically during the last 2 million years, but generally cold. There has been other cold periods of climate, especially at the end of the Carboniferous. There's a large ice age then, which actually helped cause a big mass extinction event at that time. Also, with another very cold period around about sort of 700 or 800 million years ago, where we think actually the ice could have almost completely covered the planet, but not quite. A snowball Earth hypothesis. Okay, and then conversely, there's been warm periods of climate. So, for example, on the right here, during these the Tertiary, so between sort of 65 million years and the start of the Quaternary, it was actually quite warm. So, in the sort of Eocene to sort of early Miocene, there was a warm period of climate. So, say in North America, you were having quite animals which you wouldn't have there currently, such as very large rhinos and type animals and elephants. Which are typically warmer, lower latitudes. They were found in the mid-latitudes at that point because of the warmer climate. And the very warmest climate was found in Earth's history, we know, was in the Cretaceous, the early Cretaceous period, around about 100 million years ago. Just going back to that, because I'll come back to that, why that is, it's to do with a lot of tectonic activity and a lot of volcanic eruptions during that point because of that tectonic activity, and therefore a lot of greenhouse gases being emitted via volcanoes into the Earth's atmosphere, and then therefore a huge greenhouse effect going on due to all these volcanic eruptions being very frequent back then. Okay, so warm climate at the end of the Mesozoic, it says the Cretaceous, and climate cooling since around the Oligocene. It's gradually cooled to where we are now. Long-term climate change, so it's driven partly by changes in those greenhouse gases, so carbon dioxide and methane, which is CH4. They absorb infrared energy reflected from Earth's surface, that terrestrial radiation. They absorb it, retain it, and then kind of re-radiate keep it within the atmosphere. Hence the global warming during these high greenhouse gas periods. So they exert a very strong control on climate greenhouse gases. The processes that add or remove greenhouse gases can alter climate. So, how much vegetation's on Earth can certainly alter it. That actually causes the variation in CO2 over a glacial interglacial cycle. So when you have lots of lush and more trees during a warm period, for example, there's less CO2 because it's been a lot of photosynthesis going on. But then also on the right, bottom right, it's showing how we are now, as we talked about in part one, we are now affecting global climate by production and the emissions of greenhouse gases from industry, especially from things like burning of fossil fuels and huge amounts of CO2 which are given out from that. So what causes long-term climate change? I'm going to go for a few items which do this, cause sort of natural events, natural things. So first of all, volcanic gases will trap the heat and promote global warming, such as happened in the end of the Mesozoic in the Cretaceous period. So there was a lot of rifting and expanding of mid-ocean ridges there. Basically, there was a lot of very rapid seafloor spreading going on during that period. To do with that, related to that, there's a lot of volcanic activity. Therefore, volcanoes pump out a lot of, during eruptions, greenhouse gases, carbon dioxide, sulfur dioxide, and water vapor. They actually produce a lot of water vapor during an eruption. All of those are greenhouse gases. Mountain building periods, so when you have large collision periods, say, for example, when the Himalayas were formed, and when the Alps were formed around about 50 million years ago, or sort of 40 million years ago, that may have led to this, the Cenozoic cooling, which has been going on since the Oligocene, sort of last 40 million years, 30 million years. And basically, it says here, chemical weathering absorbs CO2. More mountains, you have more weathering, and that will absorb CO2 and leads to overall climatic cooling. Other causes of long-term climate change, biological influences, for example, the formation of organic deposits removing CO2. So big coal swamps and oil and natural gas, for example, which is they will remove CO2 from the atmosphere and cause global cooling. And that's actually what happened after the Carboniferous period in Earth's history, around about 300 million years ago. We just come up in the early Carboniferous, sort of the mid part of the Carboniferous, it was a very warm period, and we had huge tropical forests, rainforests and swamps, and in those tropical swamps there were lots of organic matter building up as coal and being retained in there, basically been took out of the atmosphere and kept there, trapped in these anoxic swamps, and because of that, all that CO2 being brought out of the atmosphere, the climate on Earth swung from a warm climate very quickly. It plunged into a huge glaciation cold period, which actually caused a mass extinction at the end of the Carboniferous. Okay. So short-term climate change. The past million years has been very dramatic changes in Earth's climate related to major glaciations and separated by these shorter interglacials. The interglacials typically last from 10 to 20,000 years. Currently we're sort of 10,000 years in to the current one, which is called the Holocene interglacial. We may be about halfway through this interglacial, so in another 10,000 years we will go back into another ice age, despite global warming going on due to Earth. Certainly climate will cool significantly in about 10,000 years, which is a long time off yet. Glacials last typically around about 100,000 years. And climate shifts may occur in as little as a decade. So some of these shifts actually happen very, very quickly, as we'll see. All right, the last bullet point here is a very important point, something called climate forcing. This is basically an imposed change of Earth's energy balance. So the balance between incoming insolation, solar radiation, and outgoing energy. And that balance can change whether it's warm or whether it's cold. And there's various things can affect that balance. It's called things called climate forcing. So, example, increased volcanic activity, changes in ocean currents, and the last point, changing anthropogenic activities. So, human activity, in other words, and the production of greenhouse gases, for example. Okay, so shorter timescales, even shorter ones. So now we're talking about the last 15,000 years. There's a climate record on the right showing for the last 18,000 years in this case. And here you can see temperatures up and down below a mean of 15 degrees C here. And you can see there's peaks to the right where the higher temperatures. So in the middle part of the Holocene, which is the last 10,000 years. So a point of reference, the last glacial stage basically ended around about 10,000 years ago. So since 10,000 years ago, we've been in an interglacial, a warm interglacial, and the Holocene maximum was around about 6,000 years ago. That was the highest temperatures. There was also peaks in temperature around here. You can see a peak, and this is certainly the second part of that peak is the medieval warm period, where there were warmer temperatures. You know, people were growing crops on Greenland, which you certainly can't now. We think even vines. And then there's a current, you can just see the slither of the current warm period, human-induced since the Industrial Revolution. Troughs or peaks to the left are cold periods. So you can see at the very top is a little ice age, for example. And then going back time, there's a trough here, a cold period, where basically what happened as we came out of the last ice age, the late glacial maximum was around about 24,000 years ago, so off the chart here. Then it gradually got warmer and warmer and warmer. Then it deteriorated around about sort of 11,000 years ago. Climate deteriorated for about 1,000 years, and we call that the Younger Dryas period. And for example, in Britain, where there was an ice sheet, the British Isles, the mountain glaciers actually expanded for a bit. And all around the world, generally mountain glaciers expanded for temporarily over 1,000 years, and then retreated again as we went into the Holocene. Short-term climate changes, so you can also lump in Milankovitch cycles. So I'm not going to go through them. We've gone through those 3 cycles of recession, obliquity, and eccentricity. These all affect the amount of insolation. Changes in volcanic emissions. So as well as long-term cycles, volcanoes, individual volcanic eruptions can change short-term climate. So for example here, the Tambora eruption, the largest eruption of historic times in 1815, resulted in what's called as a year without a summer. And more recently, the Mount Pinatubo eruption, the second largest eruption of the 20th century in 1991, it says here counterbalanced global warming during 1991 and 92. Basically, the lowered temperatures for a year or two after these large eruptions, they will put a huge amount of aerosols and and particulates in ash into the atmosphere, and help reflect solar radiation and either absorb it or reflect it. So in other words, it's not getting to the ground level, which affects climate ultimately. So cooler temperatures. Ocean currents, very much on short-term cycles, will affect global climate. So here, ocean currents distribute equatorial heat to the poles generally. So they take warm water from the tropics and carry it northwards. In the Atlantic Ocean, for example, there's a strong northward movement of near-surface waters. We call it the Gulf Stream. You can see it here on this the redder colors of warm water. It comes up the east coast of America, then shoots off into the North Atlantic, heading off towards Western Europe, and keeps Western Europe, Northwest Europe, a lot warmer than what it would be for quite a high latitude. This cycle, as this warm water flows northwards, by the way, it cools, becomes saltier and denser, and sinks to the bottom, and we'll come back to that once it gets into the Arctic Ocean. And this cycle is another cycle called the thermohaline cycle related to that. It lasts about 1,000 years. So here, this red is the warm surface current, and here you can see the red Gulf Stream sort of elbowing. It goes up the east coast and across the Atlantic, up in towards past the British Isles, up into the Arctic Ocean. Once it gets up into the Arctic Ocean, it's much more cold and denser, and actually also saltier there, more saline. And more saline cold water will sink, so it sinks to depth, and then starts this deep water current of cold, salty water, which goes all the way around the planet, around the world's ocean basins. It takes about 1,000 years to go through this cycle, And there is possibly a thought that this could actually be cut off soon. We'll come back to that by the melting of fresh water in Greenland, the Greenland ice sheet specifically, and making this water not so salty because all this fresh water, pure and land-based ice water going into the world's oceans for fresh water, and diluting it. It's less salty, therefore less dense. If it's less saline, and therefore won't sink. And if it's not going to sink, it's not going to then start driving this current. Therefore, the current will be switched off. So there's a possibility of the Gulf Stream being switched off in current projections of climate change, which is a major issue for example, Europe. It would plunge Europe into a very cold temperatures if that were to happen. It's all theoretical at the moment. We don't know if it will happen, but it's a possibility. It's based on past records, these things happening in other parts of Earth's history. So that's what this slide actually is. The text I should have switched over. Disruption of currents could initiate cooling. Fresh water from melting sea ice can decrease surface water density and flow and slow down thermohaline sinking, for example, in this Arctic Ocean's sinking zone. Okay, so lastly, we're going to just talk about for the rest of the lecture, which is anthropogenic changes. So today, humans are a huge force of planetary change, as we found out in part 1 of these lectures. And that's partly due to this huge exponential population growth. So back in 2011, it's around 6.9 billion. Fast forward to say 2020, I think 2021, it's something like 7.7 or 7.8 billion. There's a billion more. So we've got it's very increasing rapidly the world's population. Therefore, there's a demand for energy, especially as all these developing world is sort of industrializing, just like the developed world did, and therefore they need power stations or they need energy. Therefore, there's a big drive. Therefore, if they're doing the traditional methods of coal power stations and the burning of fossil fuels, that's pumping out huge amounts of carbon dioxide, so greenhouse gases, into the Earth's atmosphere. So we're changing climate, and especially since the Industrial Revolution, this demand for energy with an increasing population. So we are a huge change. We're a force of planetary change, fueled by natural resources, such as especially the burning of fossil fuels, also deforestation as well, which also, as we learned last time in part 1, causes large amounts of carbon dioxide to be put into the Earth's atmosphere. So anthropogenic forcing, a type of climate forcing, is human-related climate forcing. So most important are emissions of greenhouse gases. And going back to certainly just current climate change is definitely caused by us, by human activity. Natural variability in climate doesn't explain the large increases we're now seeing in global temperatures. So here's some temperature records and some carbon dioxide records. So on the left here's temperature. It's been measured directly since 1880, or actually back to 1860, I think the first measurements. And you can see it's been rising inexorably, just onwards through the 20th century and into the current 21st century, global warming. Here on the right, you see some CO2 records. So carbon dioxide directly measured. So since the 1960s in places like Mauna Loa on Hawaii, and it's going up and up and up and up year on year. So here in 2010, it was 360, 70, 80, so nearly 390 parts per million. CO2 concentration in the Earth's atmosphere. Fast forward to around about 2020, we're now something more like we've gone over 400, so it's about 413 parts per million CO2. So it's getting more and more. Put that on a longer term time scale. So here a time scale of natural variation going back 800,000 years at the bottom of this graph. Here you'll see the sudden spike of CO2 is being observed over the last century and what's projected if you follow that trend. And we're talking about very high levels of CO2. In other words, that translates into high temperatures. That same spike here, we've seen that in part 1, so I'm not going to go too much on that slide. You saw it in the first lecture if you go back to that. And you've also seen some of these again. but just getting in this fact that global warming is caused by greenhouse gas additions to the altering the climate, especially CO2. It's steadily climbed since the mid 50s. It said, you know, CO2 was 315 parts per million in 1958. By the year 2000, it's 370. When it about I need to change some text on there. Actually, it's over. It got to 400 parts per million around about the year 2014, 2015, and now around 2020, 2021, it's around about 413 parts per million. So it's going up. It's not stopping. It's actually getting steeper the slope. Okay. So this sudden increase in temperature actually took us out of a cool phase. So since the Industrial Revolution, we were sort of plunged in the Little Ice Age. We were quickly brought out of that Little Ice Age by really the advent of the Industrial Revolution and starting the burning of fossil fuels at that time, of coal, especially. So here the pictures of ice sheets, glaciers on the right here. So global warming is accelerating the melting of ice sheets, sea ice and glaciers. And that will obviously have knock-on effects affecting communities dependent on snowmelt for water supply, for example, in places like parts of India and Nepal where they rely on that snowmelt. And glaciers are retreating worldwide. It's the famous photos from the Muir Glacier in Alaska. One took in 1941, one took 60 odd years later, 2004, and the Muir Glacier is gone. It's retreated out of shot. And that was a big red flag once you started seeing all these mountain glaciers around the world have all retreated. I think 95% of them have retreated now, big time. So places like Glacier National Park in Montana in America, by the year 2030, all those small glaciers there will have disappeared. Even in the Alps, the European Alps will be gone, we think, by the end of the century, which, is quite sad when you think about that. Caused by global warming. We're not sure. They could be gone if we don't do too much. We might be able to stop that if we decrease, if we do the best case scenario of decreasing global emissions of CO2 from industry. So ice sheets, they're retreating, but they're also getting thinner. So here's melting actually on the surface of the Greenland ice sheet. So the extent of the melting was kind of mainly just around the edge of it back in 1992. Then the darker red here, 2005, there's a larger area starting to melt. And now if you take that forward to into 2020, there'll even be more of that very high ground in the interior of Antarctica melting now. So it's around the edge because they're lower elevations. It gradually gets lower elevations on the ice. But low elevations, now they're subject to the warmer air temperatures and melting. Okay, I'm going to skip that one for to read through that slide. But then it's related to feedback loops, and there's one basically example of a what's called a positive feedback loop I'd like you to know about, which is when what drives the accelerated shrinking of ice sheets during global warming. So snow and ice reflect radiation, keeping temperatures low. So remember going back to we talked about the albedo figure. So as a percentage of how much is reflected, and very cold, it's very white, light-colored things like snow might reflect 90% of incoming solar radiation. So in other words, therefore, if it's just reflected, it's never going to be re-radiated as terrestrial radiation, therefore never cause atmospheric warming, the greenhouse effect. So, but what happens when you go into a warm period? Melting will expose the edge of where you melt the ice away, exposes the darker ground. The darker ground will absorb radiation, therefore you'll increase the temperature on Earth. Therefore, increasing the temperature will cause more melting, therefore faster the warming and increased melting occurs, and it quickly gets into this knock-on effect, this feedback cycle, where the ice sheets start to shrink back much quicker than if you didn't have this feedback. So that's leading to things like in the Arctic sea ice, the floating ice over the Arctic Ocean declines 10% in terms of area every decade. So we think this ice may be ice-free, so during the summer, by the year 2030, if trends continue. So by the year 2030, so 2030, 2040, we think summer sea ice in the Arctic will be no more. So you could actually sail to take a boat, unblocked. You could sail to the North Pole. You don't need to go off on sleds and walk across the ice to get there. During the winter, there'll still be summer sea ice, but basically during the summer, when the sea ice is at its minimum, you'll see less. And I'll come back and show you a diagram of that later on. That explains this kind of phenomenon, this feedback loop in a diagram there. So do have a look at that. And here she shows some diagrams. The top one shows the decreasing summer maximum of sea ice. So during the summer in 1980, the sea ice was covered, a large part of the Arctic Ocean. During the winter, it's completely covering all of it. But fast forward to 2012 in this case, you can see the summer sea ice is a much smaller area, and it's decreasing every year or every few years. The bottom diagrams, by the way, they show you sea ice just over a couple of years for Antarctica and kind of the relative sizes of it. So the effects of this global warming, all that ice melting, that land-based ice, critically, it has to be land-based ice melting, so not the sea ice. So land-based ice melting, it's going to go into the world's oceans. So basically, think of a bathtub, and you're turning the tap, turning the faucet, and you raising that bathtub water level up, and that's what's happening to the world's oceans. So sea level is rising. It's typically now on average around about 3.4 millimeters per year. So say 3 millimeters per year, right about 3.4. And this warming will accelerate this trend. So why is it rising? Two things. One, from melting mountain glaciers and ice sheets, and secondly, from what's called thermal expansion of the Earth's oceans. So that's also driving sea level change. It's about 50-50, the influence of each. So thermal expansion, water's a liquid. You warm it up through global warming, water will expand as you heat it, and if it expands, sea level is going to go up. So there's two processes going on. You've got thermal expansion, you've got melting of glaciers, be they ice sheets or mountain glaciers, and that water going into the world's oceans. So here's direct measurements of that. It's going back to 1880. We can measure it in the last few decades in the red line directly through satellites. Before that, it was through sort of things like tide gauges. And here's predicted levels of sea level rise. So typically, sort of minimum between sort of 20 and 60 centimeters rise by the year 2100. That's actually a little bit old data here. It's more now, we think, there's more going on. We think it's more like, which I think I'll show you in a later diagram right at the end, between 60 centimeters and 1 meter, we think, by 2100. So that's our level of sea level rise. It's always the models were basically what's happening. We're getting the very top part of the models which were made sort of 5-10 years ago. We're exceeding that almost in terms of actually what's happening in sea level rise. So say up to about 1 meter of sea level rise by the end of the century, which is a lot. Some great areas of low-lying areas of coastlines will be submerged from that. Here, if you were to kind of, worst case scenario, melt all the ice on Earth, both the Antarctic ice sheet and the Greenland ice sheet, okay, which is a bit extreme, I admit. But for example, North America, you'd raise sea level and basically submerge the whole of the eastern coastal plain up to the Appalachians, including New York and all those major cities of Washington, Philadelphia, Baltimore, etc. Big chunk of the sort of the Midwest up the Mississippi Valley, including Memphis. All of Florida were very, very quickly underwater from that. So, but that's everything. If it was just the Greenland ice sheet, most of Florida would be underwater, just the Greenland ice sheet. But still also significant parts of the coastal plain. Here, in this example for North America. The same thing would happen elsewhere in the world, on low-lying areas. That's why places like the Maldive Islands in the Indian Ocean are literally, that their existence is under threat. Um, all right, so many scientists think that global warming could lead to the interruption, as I mentioned earlier, the oceanic heat conveyor system, the thermohaline system. So a big inpush of meltwater from Greenland could dilute those saline waters, stop the sinking, therefore stop the Gulf Stream effect, basically. Also, other effects of anthropogenic change include stronger storms due to more vigorous, essentially due to higher sea surface temperatures and greater evaporation. That's why. So things like the Hurricane Katrina of 2005 that devastated New Orleans back then, that was a Category 5 hurricane, the strongest category of hurricanes. There's going to be more, and there's a trend of increasing intensity of hurricanes. So stronger hurricanes, more Category 5s with time due to global warming. Why? Because what creates a hurricane is evaporation of water in the tropics. Air rushes in to replace that evaporating warm air which rises, this moist warm air. You quickly start to get very high wind speeds, a low pressure cell developing, and then eventually an intense hurricane. So higher temperatures, high sea surface temperatures, more intense storms and hurricanes. Other things that might happen, we're talking about, deserts expanding, more arid zones, desertification, and changes in ecozones towards the poles, essentially, things moving outwards. You can see on these maps. This diagram basically tries to summarize all the effects of anthropogenic changes, be they sea level rise, be they increased storms, increased precipitation, etc., rising temperatures, all kind of summarized on this map. Last little subject is I wanted to mention the Intergovernmental Panel of Climate Change, which is the IPCC for short. It's a body under the UN umbrella, but it's essentially a collection of the world's top scientists, climate scientists from around the world, be they from North America, be they from Europe, be they from Japan, Australia, places like that, India, and they get together and they put out a report. This one's from 2013, the last one. Well, it's actually, there's one just come out this year, but it's not quite fully published yet, so we can't use the data yet. But this is from the last one, 2013, and I just want to show you some of their conclusions about climate change. And these very important reports. Something related to this year's report is something called COP26, which is happening in Glasgow in England this year, which is 2021, and that's also a very important climate change. Basically, we're trying to see what can we do about keeping down emissions of greenhouse gases. That's the key thing to stop climate change or to decrease the severity of climate change. Everybody needs to collaborate as a globe, a collection of nations, to reduce our greenhouse gas emissions. That's the key. Reduce the amount of CO2 which is going into the atmosphere, and also methane as well. So I just wanted, I'm not going to read through every line on this, but just to say some of the stuff in the red, the conclusions from the IPCC report with warming of the climate system is unequivocal. Since the 1950s, it's happening. Over the last 2 decades, the Greenland and Antarctic ice sheets have been losing mass, both on their edges and their thinning. Also, mountain glaciers are just retreating very high everywhere. That's really resulting in a sea level rise. And since the 19th century, that's been very, accelerated sea level rise. Carbon dioxide concentrations and other greenhouse gases like methane, nitrous oxide have increased to levels unprecedented over the last 800,000 years, as we can see, because we can measure that directly in ice cores, and it's never been this high. It's much higher than it's ever been before. So they've increased by about 40% since pre-industrial times. Human influence on the climate system is clear. It's not much natural variation this time that's doing this. This is something else is at play, and it's us. We are affecting climate. So it's anthropogenic forcing of the climate system. And lastly, it's extremely likely that human influence has been the dominant cause, like I say, of the observed warming since the mid-20th century. So, and limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. That's the key. That's what's causing climate change. It's greenhouse gases. It's a greenhouse effect. So we need to stop being reliant on fossil fuels if we want to stop all the detrimental negative effects of climate change, and which include increased storms, increased aridity in droughts, increased high magnitude flood events as well. Increasingly very high temperatures, sometimes dangerously high temperatures in places like the Middle East, and sea level rise, etc. So most aspects of climate change will persist for many centuries, even if emissions are stopped. We also have to accept that. So yes, there's a lag time for things to get better, if you will. But currently we're trying to, as of now, 2020, 2021, we're trying to limit the current goal is to limit global temperature rise by only 1.5 degrees by the year 2050. So rather than worst case scenario by 4 degrees, which is going to be, very negative effect. So here, some diagrams from charts from the IPCC report. This is a 2013 report, and the global average surface temperature changes. So there's different scenarios, they call them, of emission pathways. So RCP 2.6, sorry, is the best case scenario. So basically, everyone, works as a whole, and emissions are reduced. Reliance on fossil fuel burning as an energy source is reduced. We switch over to renewables as best we can. So we try to become carbon neutral, essentially. And temperatures will rise, but not much, if we can do that, which is great. That's what we want to do. But if we basically carry on as normal, carry on as we're doing, still be reliant on fossil fuels as an energy source, and all the carry on with deforestation efforts as well. It's what we call the RCP 8.5 scenario, and there you can see temperatures rise by sort of over 4 degrees, so 4.5 degrees Celsius, which is huge. That's sort of temperature rise, and that's the average. And as we'll see, that my final couple of figures show in the high latitudes, it's not 4 degrees, it's 12 degrees Celsius rise. Massive. This slide. So here the changes in average surface temperature between sort of around about the year 2000 and say let's fast forward to 2100. So the changes in degrees Celsius. If we keep to the best case scenario, RCP 2.6, we cut off our reliance on fossil fuels, for example. Yes, there is some increase, but only 1.5, maybe in the high latitudes, on average, even less than that across the globe. The RCP 8.5, if we do nothing, just say, hey, let's just carry on the way we're going, we can see temperature increases in the Arctic, for example, up to, up to 9, 10, 11 degrees, which is why the Antarctic the sea ice is melting so fast. So in other words, this global climate change, it's not the same everywhere. It's especially in the high latitudes, because there's more land in the northern hemisphere, especially the high latitudes of the northern hemisphere. Here the bottom one shows precipitation, and you show there's very high precipitation values and floods in some parts of the world with if we let climate change kind of just spiral, but also increased droughts. In other words, extremes. So the RCP 8.5, you see extreme droughts, extreme desertification, dry periods, and also in other parts of the world, extreme storms and increased precipitation. So you get very extreme weather. Also, more CO2 goes into the atmosphere, goes into the oceans, and acidifies the oceans. Carbon dioxide, is an acid. It mixes with water, produces an acid, which has a huge effect on the globe, the ocean ecology, on organisms. Some organisms can't live, like the bleaching of coral reefs. Other ones, it affects their reproductive cycle of fish and other animals, and therefore, they will dwindle in numbers. So it's these Ocean acidification is a major thing to be concerned about as well. Um, Here's showing the global mean sea level rise under the different scenarios. So the one in the blue is really what the earlier chart was showing, between sort of 0.4 and 0.6. RCP 8.5, we're talking up to a meter. And at the moment, you know, we're heading that way. We really need to change the emissions of globally. Really, by the year 2030, they need to be brought down. Even by the year 2025. So it's really the next few years are critical. Really critical, the next 10 years. So final, you'll be happy to know, this wasn't a long one again, I'm afraid. Final slide, summarizing all this in a nutshell. It is warming. What's the cause? It's us. It's not natural variation now. It hasn't stopped. It's increasing. You know, we're just there's CO2 values are rising. Because of that, temperatures are rising and sea levels rising, etc. The heat's mainly in the sea. That's where it's trapped, but that affects the air temperature above it. Sea level is rising because of all this, from melting of glaciers and from thermal expansion. The ice is shrinking. CO2 makes the sea more acidic now, so we've got acidification of the oceans. CO2 in the air, if you want a number, it's up 40% since the 1800s. It's now the highest in millions of years. We've never seen this sort of, during the natural variation of up and down CO2 levels, we've never seen it this high. The cumulative emissions set the warming. So it is the amount of emissions we're putting into the atmosphere. That is what's going to be projecting into the future how warm it's going to get. Reducing emissions will limit the warming, and that's the key. We know it will. We absolutely know it will. So there is some positivity that the world does seem to be cottoning onto that and acting. There is positive action. There needs to be more positive action, accelerated positive action, but there is a definite drive throughout the world, throughout the major economies of the world and the growing developing world, of we need to look at alternative sources of energy, especially. It's one of the main reasons. And also changes, as we mentioned in part one, about things like crops. Rice production produces a lot of CO2, traditional rice methods of agriculture with rice. So we need to change those cultivation methods of rice in particular, and that will reduce CO2. Be less reliant on livestock, be more plant-based diet is incredibly environmentally positive if that can happen. All right, I'll finish it there. Thanks for joining, and I'll see you next time. Thanks.